Giuseppe Mussardo in one line. So often when I was reading up on scientists from the Renaissance era, the medieval ages, after that, Enlightenment, there would often a word would occur to describe them, which would say that so-and-so was a polymath. I never understood what that word meant. Then I realized that people did many things in those times. There were astronomers, there were physicists, there were mathematicians, they did a lot of stuff. So there's a modern day avatar of that, that's Professor Giuseppe Mussardo. So he's an academician who wears many hats. Let's start, he made a number of very beautiful documentaries on famous scientists, 5 of them. We'll be screening one of them next Monday, Chandra, the Journey of a Star. So do come to CLT here at 5 p.m. on Monday evening. He'll say a few words about it and then go on, and then take also your questions. He is a big popularizer of science. He just told me he wrote a 600-page book on the history of quantum mechanics in Italian, which he's translating also in English on his own. And there are other books in Italian, which are also an easing model and other things, which he's, and he's deeply involved into the history of science. He's an author of the famous book, which me and I'm sure many others use in statistical field theory. So whenever we got stuck into any complicated mathematical relations and prefactors and powers, I remember looking up the book and still look on statistical field theory. And above all, he's a very versatile theoretical and accomplished theoretical physicist, widely acclaimed for many fundamental contributions in the theory of field theory and its application to a range of systems, ranging from chaos to quantum field theory, its fundamental aspects and its application to interfaces with statistical physics and condensed matter and other topics. So it's a real pleasure and an honor and a privilege to have him give the inaugural colloquium, and we're all glad that he's visiting us for an extended period for full 2 weeks. So he'll be here for this week and next week. If you'd like to interact with him, do come down and see me. With this, I won't take more of your time. He's of course also very, I mean, he's a member of many elite societies, and invited member and elected member of many societies in the world, and chairing many important Italian science decisions and higher echelons of scientific administration. And so with this, I would like to not stand between you and what seems to be a very exciting lecture. So Professor Giuseppe Mussardo, we look forward to hearing more about it.
Thank you. Thank you, Jasir. Very, very kind introduction, very kind of you. So indeed, I'm very pleased to be here. It's the first problem which has fascinating minds since now is 170 years. And without you to get excited and jump on the chair, I'm not going to prove Riemann hypothesis. So calm down. But I'm going to argue strongly that physics suggests a very, very natural scenario for the problem. And this, I hope, way to go. So the topic of today will be, I will expose you to an elusive enigma that will pose us several questions and several interesting questions. Then I would like you to ponder about the, how to say, contradiction, the tension which exists between proof and truth, which is a serious business in science, and I would say also in other fields as well. And then after that, I'm going to introduce you to the problem of Riemann zeros, and more important, to friends, which are the Dirichlet zeros. And then once again another big tension, the big tension about randomness versus determinism, which at the end of the day we'll see that are not so contradictory one to the other. And then I will expose you to the art of experimental mathematics, and finally will tell you for whom the bell tolls. So this topic I face in several papers with close friend and collaborators, who is André Leclerc. So we publish several articles. You might look at them for details of what I'm going to tell you today. So the story, probably here, there is a resonance with the microphone, at least with this, this one. So I have to say, the story, as a matter of fact, historically centered in Göttingen. Somehow Gauss started first, second was Riemann, and then we'll see Dirichlet as well. So in a way, now in another is always centered in Göttingen. So what is the problem? The problem is Riemann in 1859, I will tell you later, come up with a function in the complex plane that apparently, when he tried to compute the first zeros, display themselves along the line 1/2. So it seems a very remarkable fact, and indeed they start the story of the Riemann hypothesis, namely whether if indeed all the zeros are there. However, immediately later, people have found another function, which technically speaking is called Dirichlet L1, you will understand the notation later, which as well as the zero there. And then, not even time to say, wow, you find another one, always 0, 1/2. And then you find another one, and then you find another one, and so on and so forth. So in short, there are infinitely many different functions that are all related to number theory. So this is another beautiful tension. Number theory is discrete mathematics, while I'm talking here continuous function, and moreover the continuous function par excellence, the complex function. And all these functions related to number theory seems to have all their line displayed on the real part of S equal 1/2. Now I have to be clear. All these functions has the same as SISSA, 1/2, but the location of the zeros along this line are different one from the other. It's not the same. Each function has their own pattern of zeros. The only thing which has in common is that they are lying along the line 1/2. So this is the phenomena which get used as the generalized Riemann hypothesis. And this has to be clear. Namely, Riemann is only one of infinitely many examples. So somehow get the credit, get the fame, get the notoriety by just a teeny tip in a huge continent of function which has all the same displacement. And actually, this is what creates the fatal attraction, at least for a person like me. Namely, we know that a basic fact in physics consists of universality. Universality means that you might have different systems which are really microscopic different as you can imagine, which nevertheless share the same universal behavior independently of their microscopic details. So this is all the beautiful subject of phase transitions, in which, for instance, a system like water, here is the phase diagram of water, or system like Z2 magnetic field, at the end of the day, if you properly scale the variable, admit always the same identical critical behavior, okay? So this is what physicists elaborate in the 1950 and later on, and was understood really in full glory, and is one of the main chapters of modern theoretical physics. So that being said, the idea that a remarkable mathematical property as the one I've shown you, namely there are many, many different functions which always has the same behavior, might be understood from simple and elegant requirement of physical system is really too appeal to let it by, okay? So I want to say that when you see the phenomena I just showed, when I myself I saw the first time, I immediately react, say, well, there should be a simple reason for that, okay? So this is what I'm aiming to show you, this simple reason. Now, of course, I owe you a physicist apology. Now, understanding, of course, is very different from proving. So just to make a simple statement, Copernicus understood that the solar system was much easier to understand if you take the heliocentrum system, but he never proved it. He was unable to prove it. So, and this is the difference which really is about the tension which exists from a physicist and a mathematician. So the way we see such a physical approach, the way at least I saw it, is really as an exploratory tool to discover mathematical truth, to point something, and hoping that this will be the starting point for more formal approach and probably the final crack to the problem. Now, to make even clear this point, let me bring you to this dichotomy between theories and theorem, which we always give for granted, but might require a minute of thought. So what is the difference between that? If you see such an equation, of course this is not a theorem, this is a theory. And once you get it, well, all the richness of cosmos display to you. But you never prove it, that equation. You just take it. It was a statement of commitment. Now, if you take this other equation, that Maxwell never proved it, well, once you take it for granted, you can explain essentially all phenomena of electromagnetism. And finally, since it's the year of quantum mechanics, if you take this equation that Schrödinger never proved it, well, at this point, all the weird phenomena of quantum mechanics will be at your foot. So let me give you a paradigmatic example of this attitude of a theoretical physicist to address a mathematical problem. The example is very, very simple. The example is, take the so-called square-free numbers. You know that any integer number can be decomposed in primes. Now, the square-free numbers are those which never have one prime more than one, okay? So, in the prime decomposition, the primes which appear only one times. So, just to make clear, 5 is a square-free numbers, 6 is a square-free numbers, although it's not prime number, and 30 is a square-free numbers, because are made of 3 different primes, but 9 is not, okay? Now, that being said, the entity is defined very clearly. Let me pose the problem. What is the density of square-free numbers among the integers? Now, how many times I find a square-free numbers among the integers? So this is a well-posed mathematical problem. As a physicist, you could argue like this. Assuming that there are no correlations between prime numbers, of course, 1 over p is a prime number, is the probability that a generic integer x is divisible by the prime p. This is very simple because each pre-p number you find a prime. So you rephrasing the deterministic fact that you find a prime p in a probabilistic one, saying 1 over p is the probability that the guy is not divisible by p. At this point, once I took this, I never prove it, but once I assume this, 1 minus 1 over p squared is the probability that a number x is not divisible by the prime p more than one time. Okay? So I'm forced to do that. At this point, what is the probability that I have hidden square-free numbers? It's just the product of this probability, assuming that there are no correlations. But at this point is a theorem though, because this infinite product, this is a theorem, it's just the inverse of the Riemann computed in 2. This is a theorem, this value is 6 over pi square, and then you get a bold number. So I'm saying that out of probably shake it hypothesis, at the very end, I got a prediction. And then as a physicist, I make experiment, okay? What I do, I just listed the integers, and I just canceling the square-free numbers. And I just check how many times remain in these sequences, plotting their corresponding density. Of course, I cannot assume, how to say, that always get through, but asymptotically, you get that the density is indeed 6 over pi square. Okay? So I hope you appreciate the things. I assume things, I never prove it. But then I'm forced, how to say, the theory forced me to do that. At the end, I get a bold result. At the end, I do experiment. So this is the circle of physics, in a way. So this is essentially what I'm going to do later for sharing some property of this function. But first, let me introduce you, Dr. Riemann. Now, Dr. Riemann was a very shy person that was a son of a Lutheran minister, and he was supposed to become minister as well. So he enrolled in the theology faculty in Göttingen, but then he had the chance to cross Gauss, and his life changed completely. So I get completely involved in the fashion and the charm of mathematics, and his PhD thesis was the complex analysis that we know by now, okay? Now from there, he moved to Berlin, and then later on, in 1957, come back to Berlin, to Göttingen again, actually to take the chair of Gauss that was dead at that time. And 1859 was his annus mirabilis. So he was again elected to the Academy of Science of Berlin, and then he has to produce a paper, a manuscript, for that occasion. And this was the first page of that paper, in which, for those of you that read German, essentially say of the amount of primes less than a given number. And one can recognize actually formula like gamma function and things like that. Now, at page 6 of this manuscript, you find the famous sentences. He says it's very probable that they are all along this line. Of course, it would be desirable to have a rigorous proof of that. However, I do not have time, and I keep going. For what I have to say doesn't matter, essentially. Well, it matters, as a matter of fact, but at that time, you know the story, Siegel, years later, have a possibility to have a look at the paper of Riemann and realize that he has developed what is called today Riemann-Siegel formula. That is one way of really computing efficiently the zeros. So Riemann has computed essentially 3 zeros, and he found out that, amazingly enough, they align along the line 1/2. So this was his conjecture, say, wait, seems to be along the line 1/2, probably they are all over there, and so this is how the story starts. Now let's introduce one of our main actor here, the Riemann zeta function. As a matter of fact, this identity was already known to Euler, and indeed it's called Euler identity. So this function, the complex variable s, nicely enough admit two different representations, as an infinite sum on the integers or as an infinite product on primes. So this is why this function knows about the prime distribution, and this was the reason why Riemann was behind this function. Today I have no time to go in these branches because otherwise my lecture will diverge, but whoever will be interested in this story, please contact me in the next days. I will be very pleased to tell you what it's about. Now, the proof of this is very simple, because this binomial, this 1 over p is always less than 1/2, so you can develop in series, and when you collect all possible terms coming from this infinite product, you realize that the most general term on the denominator are of the form product of prime with arbitrary power, because you can collect from any p all the powers you like it. Since exists the Euclid theorem that any integer number admit one and only one factorization in terms of primes, you realize immediately that what is here is here, because at the end the most generic term here is an integer, and therefore is what is left on the left-hand side. Now, in the eyes of a physicist, this identity is very remarkable, because it's the identity of partition functions. Now, imagine that you have on the left-hand side free bosonic system that has a dispersion relation, the logarithmic of the prime. Okay? Now, being bosonic, of course, the levels can be occupied in all possible ways. I have not to tell here, right? So it's and therefore, when you do that, you realize that if you take shell of energy in terms of the integers, you can express the partition function ensemble either in terms of grand canonical ensemble or in terms of microcanonical ensemble. Now, for a system which has this dispersion relation, unfortunately, the density of states grows exponentially. So it exists at temperature. Actually, I forgot to say that the variable S in physics term assume the interpretation of the inverse of temperature. So as I said, since the density of states for a system with that dispersion relation grows very, very fast, exists a temperature where the energy cannot keep the entropy bounded any longer and the system diverges. In physics, it's called Hagedorn temperature, and this happens in all systems which has this characteristic. For instance, string theory is one system like that. So, all to say that Riemann zeta function as partition function is intrinsically defined in low temperature phases. And you might ask, what is high temperature phases of this system? How can I define that? So we need the analytic continuation. But Riemann invented, so he was the master of analytic continuation. So for him was really trivial exercise to find an equivalent representation of the function with a proper contour in the complex plane. And this was enough for him to derive the desired functional equation, which allowed us to get values on this part of the plane in terms of values of beyond the real part of S equal 1. And with this formula alone, notice that here there are very well-known functions. The sinus has zeros in all possible integers, but here there are half integers, the frequency, and gamma function, you know, has a pole in all the negative part. So all to say that this part here is responsible for the so-called trivial zeros of the Riemann in all the negative even part, -2, -4, -6, and so on. And Riemann proved that, on the other hand, in the so-called critical strip, which is between 0 and 1, there must be infinite number of zeros. I'm telling you how he arrived to these conclusions. And as I said, he conjectured that these zeros, not only there are infinite, this is not conjecture, it's a theorem, but he conjectured that all the zeros in this strip are aligned along this line. Now, how we can prove that there were infinite number of zeros? Well, first of all, you can cook this relation defining a new function. Sorry, here I forgot a hat, which absorb essentially this term here, and making the function without any major complicances to look really invariant with respect this axis. So the invariance is like this, or like this. So the function is completely dual with respect to the axis 1/2. So this means if there is a zeros outside the axis here, there must be a zeros displayed in this other way, and vice versa, it is the other way around. Now, how he computed the number of zeros in the critical strip? He realized that this was the number of zeros where t is the height, and you see more you go high in this critical strip, more zeros you have with this spatial density. The density is logarithmic t over 2 pi e. How he did so? In a very simple way. He computed the logarithmic residue of the function, which always compute the difference between zeros and pole of the function. But the pole is the only pole in 1, so therefore, subtracting 1, what he get was the number of zeros in that strip. Okay? So, summarizing, Riemann knew that there were infinite number of zeros in this strip. He checked the first 3 was along the line 1/2, and then he said, well, probably all the others are on the line 1/2. Now, many people really was challenged by this result and start to compute these zeros. So this is really partial list of many of the people involved in this kind of race. And I want to also draw your attention on Turing, that he didn't believe in Riemann hypothesis, and he constructed his own machine, and finally was able to compute 1,104 zeros, disappointingly realizing that they are all on the line 1/2. Nowadays, it has become really a race, and people have really checked even more numerical algorithm against this problem, arrived to 1 billion of these zeros. No one is ever been found away from the axis 1/2. So these are the first one that are displayed there. So the first is 1/2 plus 14.13 plus 21, blah, 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 blah. Okay, so this is the mathematical problem. Let me tell you the physical approaches I'm gonna present to make certain progress on this problem. There will be 2 different physical approaches, one which is a random walk, and the other which is Bethe ansatz quantization. So let me start from the first one. Now, random walk, as you know, is the phenomena observed by the Scottish botanist Robert Brown at the beginning of the 18th century, 1824, where some pollen put in water, he saw there were endless motion. He was very, very puzzled by that. So he tried to do many, many things, even to go to Louvre and taking some dead pieces from the mumia, because he thought that this was kind of vitalism, some kind of, so he was really puzzled by all this, and he never realized what was going on. So we have to wait, indeed, for the most famous clerk of patent office of history, Albert Einstein, to realize what was going on. And Albert Einstein, you know, has a very peculiar style. He was like a surgeon. So he just picked up the most important things in a very, very direct way. So in a paper that is very few pages long, although he developed later, he said, listen guy, what you have under your eyes is the proof that exist atoms. At the beginning of 19th century, this was a controversial, this was heresy. And people like Boltzmann suffer a lot that people didn't get through the atomist theory. Einstein said, look, what you are observing is essentially the movement of atoms, which are so microscopic that heat handles these huge piece of materials, which are like a montgolfier in a kindergarten, get heated by all the kids, and therefore has a random motion. And he was able to relate the mean displacement of this particle to basic atomic quantity, like R is the constant of gases, T is the temperature, eta was the viscosity, A was the dimension of this atom, and Na was the Avogadro numbers. So knowing the Avogadro number was as much as say the atom exists, and this is their numbers. And this means that the Brownian motion has a universal displacement which goes with 1/2. So I would like to convince you that 1/2, which is written in marble, so in random motion, you cannot change this 1/2 by any epsilon, is 1/2. This 1/2 is what rule the zeros of infinite number of functions. So this is my claim, okay? I'm giving you an argument why the random motion is associated to the problem of Riemann, or better, Dirichlet. So as a matter of fact, this bold prediction by Einstein was put to a test by Jean Perrin in 1912 that get later the Nobel Prize for it. And what Jean Perrin did was a statistical analysis based on really equilibrium situation. So he take many trajectory and he average on them. Now what is important for my sides is that some years later, and actually Jean Perrin arrived to a very net determination of the Avogadro number. What is crucial for my consideration is that some year later, a Swedish physicist, Ivo Nordlund, were able to arrive to the same Avogadro number, but using just a single Brownian motion trajectory. So what he did, he made several snapshots of the trajectory. So essentially make a Mercurius drop, and then the drop was going down. It takes several shots, and therefore for statistical physicists is when you interchange equilibrium average with time average. And this hold if you ever go DCT, okay? And done this, he arrived exactly to the same Avogadro numbers. So you will see later that this is the things I have to use to argue about the physicist approach to the Dirichlet Riemann. Indeed, let me tell you the idea that is behind. The idea is that I'm able to show that to any Dirichlet function, I can associate a random walk, different one from the other, okay? Although, nevertheless, the overall envelope is always square root of n, okay? So the idea is each function corresponds to different representative of Brownian motion, but all of them, for the fact that being Brownian motion, diverge like square root of n, and therefore give rise to a beautiful normal distributions. And moreover, the approach, the physical approach I'm going to show you, allow you even to control the subleading log n correction that is well known in Riemann to exist. Okay? So this is the claim. This I will do in the first part. I will argue that the infinitely many Dirichlet function correspond to the infinitely many random walk realization. Nevertheless, all of them diverge square root of n. And then you will see where this 1/2 will come from Mellin transform. Now imagine that I've been able to argue that, sure.
Where does the log n come from?
The log in Riemann formulation is always put in the statement that the zeros are 1/2 plus epsilon. There is the famous epsilon. This is a mathematical term. If you want an answer in physical term, when you say the random motion goes like square root of t, actually is a shortcut answer because this is the mean. If you are on the other hand interested in the full distribution, you have rare event that you have to take into account. This is the log-log correction. Okay? So you will see how it come up naturally, this term. Now imagine that I'm able to show that indeed all these zeros are on the line 1/2. And now you become more ambitious. Say, okay, can I compute now where are they along the line 1/2? To do that, I have to use another trick of physicists, dirty trick of physicists, which is the Bethe ansatz quantization. Now, Bethe ansatz quantization essentially is a way of getting the discrete part of a spectrum of a theory which live in a finite volume, said in short. So this was invented by Hans Bethe in 1931 and is becoming an incredibly popular method in condensed matter, in statistical physics, and so on. And years later, when there was the anniversary of Bethe, a colleague of mine went and interviewed Bethe. Say, so Professor Bethe, how come you invented the Bethe ansatz? He said, Bethe what? He forgot completely what he has done in 1931, okay? So nevertheless, this is important and amazing, simple formulas to get energies. So imagine I have a free particle on a circle, therefore I have really wave function here. And imagine that I have impurity along this circle, which are purely reflective, with some S matrix, okay? So Bethe ansatz is the following requirement. I get the particle go around the circle, of course accumulate phases all around, but finally come back to the same point. So you have a quantization condition which is this. The phases of the free wave times the phases acquired by all the defect which are there has to be +1 or -1 depending is the particular balls or fermions. If you take the log of this equation, you get a highly non-linear equation for the momenta, and from the momenta you get energy, okay? So I'm gonna show you, hopefully I will have time, that I can get exactly the spectrum of the Riemann and the Dirichlet, namely these values, 14.21, whatever they are. I can get exactly all these values using Bethe ansatz. Okay? So there are, summarizing, two physics approaches. One, we somehow argue strongly that the zeros has to be on the line 1/2. And the other one, once I know that there are on the line 1/2, I have a way of computing their imaginary part. Okay, so let me start from the first part, alias Riemann and Dirichlet. And this I can entitle Primes in Arithmetic Progressions. So Dirichlet, that was the master of Riemann, posed this very, very simple problem. He said, take an integer q, which is called modulus, and take another integer h, which is called the residue, and let n run on all the integers. So this is an arithmetic progression, and he asked the question, when it happens that along the sequence I have infinitely many primes, and the answer is stunningly simple, you have infinitely many primes as far as q and h are coprimes, meaning they do not share any common divisor. This is necessary and sufficient conditions. So, let me just give some example. In this formulation, the Riemann problem just is the simplest of these sequences, which consist modulus is equal 1, and you are counting how many primes there are along the natural numbers. But Dirichlet can pose any modulus you like. You have infinite choice of Q and H that you can play with. So for instance, imagine I choose 5n plus 3. I make all the integers generate in that way, and then I found many primes that appear in the sequences. And Dirichlet showed that there are infinitely many. So you change the modulus, you change the residue, you find many primes on that. Now, a geometrical way of showing this is, imagine I take the modulus 5. Of course, I have 4 possible residue, and then I can start see where the primes appear. So it will be here, the first one, there, 13, 19, and you keep going, and so on and so forth. Now, stories start to become more evident if you increase the scale, because then you start appreciating that there will be essentially an equal number of density all over the residue class. This will become a theorem. Dirichlet proved that the density along any residue, once you fix the module, is the same. Okay? It's called the Dirichlet theorem. So what Dirichlet is doing is essentially condensed matter on integers. What I mean is he put a lattice on the integer axis and he make arithmetics modulus Q with periodicity. So it's like a clock in which we count hours modulus 12. However, to have a nice arithmetics, you cannot use all the digits between 1 and 12, but you have to select all the coprimes of them, 1, 5, 7, 11. Why? Because you want to have a nice group structure. And this is called the multiplication of the numbers modulus 12. So for instance, 5 times 5 is 25, modulus 12 is 1. 5 times 7, modulus 12 is 11, and so on and so forth. You might ask, why don't you use also the other numbers? Well, for very good reason, because if I take 2, 2 times 2 is 4. But 2 times 8, modulus 12 is also 4. But we know that group has to be invertible. So, if I choose all the number, I do not have a structure which is a group. So at this point, this group, which is simple as it is, get a very Haulich name. It's called the abelian group of prime residue class modulus Q, and consists of all the numbers which are coprime with a given modulus. The number of elements is a very interesting number theory function that was computed by Euler, and is given by this product on all the prime which divide the modulus Q. Now this formula is very simple to use. If you take modulus a prime, the number of elements of this group is Q minus 1. If you take a number which is composite, like 20, you have to compute phi of 20, which is 8, and there, this is the order of the group. Now this group is abelian, so I have to remind you some very basic things of group theory. Remember that a abelian group has as many classes as elements. Representation theory say you have as many reducible representations as classes. So in these cases, they are one-dimensional because they are abelian, and there are as many as the group element. Therefore, this one-dimensional representation can be only phases, because are numbers, complex numbers, and their number is equal to the order of the group that was this Euler function. Now this arithmetic function, which is called Dirichlet characters, satisfy many simple properties. They have to be periodic, of course, this is the way they were defined. They are purely multiplicative. They are different from 0 only if n are coprime with q. And moreover, being a finite group, if you take one element, you keep going, you find out the identity. Therefore, these numbers has to be roots of unity. So simple as this. Let me give you an example. Imagine I take q is equal 7, the number of element is 6, the root of 6 is displayed here. So this means that the 6 characters can be expressed in terms of omega. And this is indeed the character table for q equals 7. So you have to read like this, and finally 0, and I keep going periodically. Notice that in any character table there is always the trivial representation which is made by only 1. Sometimes there are real characters, but it's not guaranteed, but usually are made of roots of unit. Okay, so with these preliminary things, Dirichlet come and say, now let me define my functions. And he defined a function which is closely related to Riemann in terms of this character. So they are series of the type 1 over ns, but the coefficients are the characters. Since the characters are multiplicative function, you can put in this form in terms of primes. The proof is exactly like the one before. And these functions are made of this character which are phases. For any modulus, there are a certain number of different functions defined in this way. And what are the properties of this function? Well, from physics point of view, they are partition function of free bosons with some abelian extra charges. But from the mathematical point of view, please appreciate the fact that the Riemann is just a very, very, very special case of this Dirichlet function, which consists of the fact that you choose the module to be 1. But Dirichlet say you can choose any modulus of the Earth, and you will have function of this type. It's interesting to compute the residue of this function, and the result is different from 0 if you are taking the Dirichlet with principal character. For all other cases, you get zeros because you get the sum of all the root of identity which sum up to 0. Okay? So, for what the zeros are concerned, it's useful to consider two different cases, the L function principal character and L function non-principal characters. This is a distinction at the very pedagogical level. There is nothing basic here. It's just to show you in a very simple setting how the story goes, because with a better insight, the two cases are essentially the same. The difference from physical point of view is if you have a Brownian motion with 0 average, or if you have a Brownian motion with drift. So Dirichlet is the most complicated one, because you have to distinguish the fluctuation, but in something which is growing, okay? But there is no main things. So let me dub Tolstoy saying every happy family is happy in its own way. All unhappy family are the same. Of course, Tolstoy is vice versa. But let me say what I mean by that. What I mean is, for what concerns the Riemann hypothesis, the L function principal characters are equivalent to prove Riemann. Because if you take principal character is 1, so you get infinite product on all the prime which do not divide Q. But then you can complete this infinite product, multiply all prime, and get the Riemann zeros with this extra term. Since there are a finite number of them, they never have zeros, you immediately conclude that this function, Riemann, has exactly the same zeros. So if you prove Riemann hypothesis for Riemann, you prove for all the Dirichlet with principal character, and vice versa. On the other hand, the non-principal character is very, very nice to work with because they are entire functions. entire function in the complex plane is the best you can ask. Function just fixed by zeros, nothing else. So this function has no pole. I told you the residue is 0 here because the sum of root is 0. So there are only zeros in the complex plane. And therefore, I would like to address this one, giving first a quick summary. So Dirichlet defined this function in terms of this character. These hold because they satisfy all the property we need. There is duality as before. You can check all this. These functions are real on the real axis, are real along the 1/2 axis, and so on and so forth. And moreover, the number of zeros in the critical axis you compute exactly the same way, so I'm going a bit fast. And at the end, you get that the only difference with respect to previous equation is the presence here of the modulus, okay? But that's it. So the generalized Riemann hypothesis that apparently was put forward by Peirce in 1834 claims that all the non-trivial zero of the Dirichlet function for any modulus or any character are all along the critical line placed to 1/2. So this gives really the overall picture. And so let me now tackle this problem with some consideration of randomness versus determinism. Now you might be puzzled because I'm talking about number theory. And number theory usually is considered as a field really ruled by military rules where randomness seems to play no role. Well, you have to read this beautiful book by Mark Katz to convince you otherwise. There are endless number of examples where randomness and probability play a very, very important role. Let me give you a few examples just to appreciate the things. I would like to tell you some arithmetic tales from the world of pi and the strange realm of large integer numbers. Now, pi probably is the most elegant number that we know and admit fantastic elegant formula like the one here, which of course I have not to tell you who was the author, or infinite product of radicals, or even a series in terms of Fibonacci. So there are endless number of formulas which show what? Regularity. Something which seems completely deterministic. On the other hand, imagine I go to the digit of pi. I can take any basis. I do here in the usual digital one, the decimal one, and then I start doing statistic on them. I ask, sorry, how many digits of 3 I have in these decades? How many digits of 5? And so on and so forth. I count. What happens? Completely flat distribution. Of course, with some fluctuation, but which are completely normal. Then you say, okay, now let me take, for instance, a digit in period of 6. I can choose any other period. Let me do the statistics of this digit. What it is? Once again, flat. Okay, let me take a digit randomly of pi. What is the statistics? Once again, flat. So the number is as random as you can imagine. No structure whatsoever. And this is proved physics-wise, making just a standard analysis. You take the average of this displacement, you compute this displacement function, and you distributed it. What it is? Gaussian. Okay? So we have simultaneously the most ordered number of mathematics and the most disordered one at the same time. Now let me take another example where probability play a very important role. Imagine you take this arithmetic function. You take an integer, you make the prime decomposition, and you just consider how many different primes you have in the decomposition without caring the power. So in this case, there were kappa of them. I would assign to this integer omega n equal kappa. Completely deterministic function. You give me a number, I make the prime decomposition, I assign omega kappa. But then you can start saying, I don't know where this number comes from. Can I get something of it? Okay, go to very, very, very large number and start plotting these guys here. You find sequences which are completely random. You cannot predict what will be the next. Okay? Now, with a certain insight, you will realize that the average of this quantity is log n. In number theory, always turns out log n. This means something stunning. Means that if you take integer of this order, 10 to the 1,000, this number in average are made just by 7 primes. 7. Okay? Something amazing. You do the distributions in terms of this variable, and what you get, normal distributed. So this is, as a name, is called Erdős-Katz theorem. So once again, you get a very deterministic function, but when you look at it in a broad sense, random distribution appear. Okay? So with these ideas, I would like to show you that there are randomness in the Dirichlet function, which are military function, are ruled in this way. And I have to appeal to a remarkable theorem of two mathematicians of the 15th, Grosswald and Schnitzer, that they say the following. The theory is really stunning. They say, take the ordinary Dirichlet function you like, any character here. Define in terms of product. Here are the primes. And define a fake Dirichlet where you make a product of integers which are not primes, but are random integers always within these intervals. Remember that the intervals of primes can get as large as you want, can get as log of n. So there are infinitely many functions that you can construct in this way. And then the theorem says this function and this has exactly the same zeros. How we can prove it is very simple. Since this integer grows as the prime, the ratio of this function is never 0. This is a basic theorem of analysis. Therefore, written in this way, since the ratio is never 0, wherever one is 0, also the other is 0. But this is fantastic, because I have to show where the zeros are. I don't care about the function. But now I have a setting. I have a probabilistic function to work with. Okay? Actually, when I saw this theorem the first time, I cannot believe my eyes. And then I say, well, I mean, how come? And then I make some experiment. So this is one of my early experiments. This is the modulus of Dirichlet, which has very distinguished zeros. And then I take this Grosswald-Schnitzer function with probably 500 terms, not even infinite. It jiggles around the complex plane, but then ping, 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 it pin exactly the same zeros. Okay? So then we are in a good shape, because at this point I have a probability theorem to work with. So I said I could do the Riemann, but Riemann is tough. I'm going to give for you the argument for the simplest case, which is Dirichlet. So what is the argument? The argument is this. I take from Dirichlet the product representation. So don't get full, before I denoted L, Dirichlet function L. By the way, L stands for Lejeune, was the name of Dirichlet. I call P here because I'm referring to the product representation of Dirichlet. Okay? And I will look to enlarge the domain of convergence of this property, which originally is defined by real part of S bigger than 1. So I take the log of this, and then we ask ourselves, when the log of a function is singular in two places, where the function is 0 or where the function is infinity. Now, Riemann never get infinity, so at least in this finite region of the plane. So log of P is the ideal diagnosis to check where the zeros are, okay? And now, I'm gonna see the singularity of this function, where it is, and I use the usual convention that people write S like sigma plus IT. So when you develop the P, the log of this, the term which rule the convergence of this log is exactly this term here. Now look how it looks like. Is the sum of character but on prime sequences. And here are primes. Now this is a theorem of mathematics that any Dirichlet series, like this one, you can always write like a Mellin transform, as far as you have an appropriate density. And what is the density? Is exactly the sum of the cosine of the theta term. Remember, the character was exponential I theta, but computed on primes. These are completely crucial story. This density is computed on the sequence of primes. So what is the strategy? The strategy is I have this function which is naturally defined in this part of the plane, and I'm trying to see how much I can push in the complex plane before I get stopped. And when I get stopped from the first zeros, no matter how high the zero is. I don't care. I'm only sensitive to the real part, because this is the property of the Mellin transform. So I will be blocked by this. So if I'm able to show you that I can analytically continue this series up to the line 1/2, since I have duality of the zeros, I can claim that all the zeros are on the line 1/2. Now I would like to underline that Hardy, the famous mathematician, was able to prove that an infinite number of zeros was on the line 1/2, but not all. Okay? Here, if one can get through this argument, can show that there are all, because there are duality. So if I can arrive to 1/2, I never miss any one of them. So how to show this result? Well, if the density, which is here, goes like square root of half, you see immediately that the integral diverges precisely the real part of S equal 1/2. So what I have to prove is that this density m of x diverge like square root of x. This is what I have to do, okay? Now let me also do a remark here. Imagine that my density diverge like square root of x n with some log correction. Do this spoil my argument? Not at all. Because in Mellin, any log never change the location of the pole, but only the residue. So any function like this has always the pole in 1/2, and the residue is changed by the presence of the log, okay? And so, where is the randomness of the infinite remaining Dirichlet function? Now look the story how it goes. Imagine I take the sequence of natural numbers, and I compute the residue of them. The story is absolutely boring, because, sorry. So if I am on the integers, the residue is very boring. I take residue 7 here. Will be 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, absolutely boring. But the story changed completely if I'm asking what is the residue on the sequence of primes. So I get 2, 3, 5, 4, 6, what is this, 3, 5, 2, and so on and so forth. So when you start seeing in large, you get a sequence of numbers that you cannot predict. It's a sequence which looks completely random. It's not random. If you knew it, you can predict it. But if you see under your eyes, it's a pseudo-random. Can you really prove these kind of things? Well, this is the hard problem, to show that this sequence indeed is completely random. So what is the problem? I have to control this series made of cosine of angle, but computed on primes. So first of all, let me plot this function. look how it looks like. If I go to prime, get completely crazy. Okay? If I make the sum for many Dirichlet, it looks like this. If I normalize square root of n, they are indistinguishable by any random motion you can construct yourself. Hence, the property of this series is, first of all, it's made of terms of order 1. This is important because in statistical mechanics we have what is called Lévy flight. Means that with one term, like birds, I can arrive very far. Okay? Here, if you want to arrive very far, you have to sum coherently term by term. So all of them is order 1. All the angles are equiprobable. This was the Dirichlet theorem I mentioned before. And if you do not believe it, you can make the statistics yourself, and you find stunning flatness of distribution. And therefore, I'm essentially playing with dice. I'm playing with dice of Q phases, nothing else. Okay? So, the mean of the series is 0, in this case, it's just a theorem by Dirichlet. And then you might say, are they weakly correlated? Well, you have tools to check this. You can make correlation function. So I did it numerically, and look how it looks like. Look, delta correlated. 1 in 0, almost 0 there. But then, I mean, you say, but really 0. In physics, never exists 0. So let me see what's going on here. You enlarge, and what you find? Non-zero. Something which is small and fluctuate and so on. You know what they are? Finite size correction. Very well known to physicists. This means that if you make your statistics on a finite ensemble of numbers, people, Lemke, Olivier, and Sundararajan, very important and famous mathematician, solved the following problem. You have the sequence of prime, and you ask, I have a residue here of certain type. What is the probability that I will get a residue to the next prime, or to the prime which leave kappa steps behind? They found these correlations. Let me give you here. So they say the probability, the frequencies that you get two equal residue at distance kappa is dictated by the Euler function and some term that you see n is the size of your sample. So there is an explicit dependence on there. And you can check that indeed all the correlation I have depends on this term here. But this term vanished when you go to infinity. At to infinity, all the residues are uncorrelated. So at this point, this series should have all property of Brownian motion, alias the average is 0, all the momenta satisfy just the usual statistical Brownian motion. Okay? Now, the log-log correction, there is a very important theorem by Kinching-Kolmogorov that say for a Brownian motion, the soup of the displacement goes like square root of n log L. These are the rare events. Okay? So this is where the log come. And so at this point, all these functions you predict, you foresee that must satisfy this. And you can look it directly. So probably I'm a bit off. So just let me flash the first things. So imagine I arrive to this conclusion with the argument I gave, but let me play the role of Sam Thomas. Let me put the finger on it, okay? I would like to check. So I would like to check that this series goes like this. How can I do it? Well, you can never confirm a physical law, but you can falsify it. So I can generate endless term of this series, and then I can sample it chopping. Means I take this series, which are infinitely long, and I take large subsystem of that, making stroboscopic analysis of them. So I'm doing like Nordlund things, and checking all these things. I can do in infinitely many ways. I've done this analysis for millions of trials, never found a single violation of this law, and I can quantify it, and I can go forever with this analysis. So let me show you a few examples of that. I can compute the variance for any Dirichlet function, and I can take care of the finite size effect and so on and so forth. I can plot it for any of them. The prediction is that for any modulus should be a straight line. I change the Dirichlet, straight line. Change the Dirichlet, straight line. Change the Dirichlet, straight line. Always. No violation of that type. What is the confidence of this test? The confidence is Kolmogorov's-Smirnov test, which is 99.99%. He says you are right in the 99.99% of the cases. You can do many statistical tests to check whether the sequence is random or not. I made all of them. And as I said, I repeated millions of times, never find any single contradiction. So let me show you the last one, and then I finish. Imagine I take a sample of this, and I pretend to be part of a Brownian motion. So in any Brownian motion, you have the time mean, where it reached the minimum, the max, and the difference of this time. Of course, these are random variables, ruled by a probability distribution. This is given, theory, and then I make my experiment. These are my experiment, my histogram. What is the likeliness of my fit? The likeliness of my fit is 99.99%. You take the distribution of the difference, which are much more complicated function. You make, once again, the analysis, and you find, once again, a stunning agreement with the data. You make the distribution of all this stroboscopic part, perfect, normal wave, normal distributions. And therefore, the disorder always give rise to this log term. Yeah, it's true. As I said, here the origin is very simple, come from probability, nothing else. Because you want to say, really, what is the probability I can really arrive to infinity? So the average is square root of n, but then there are the rare events, and Kolmogorov keep track of them, arrive to this correction. Actually, it's very, I would say, very, I don't know to say, funny story about the Riemann. You know, there is what is called Mertens conjecture. Mertens, that was a mathematician of the previous century, says if the residue of the inverse is really a Brownian motion, I prove the Riemann, okay? Now, people make this sum and write to a theorem, to my eyes is sensational, say, no, this sum is never bounded, it's always bigger than 1, so Mertens is wrong. I mean, any Brownian motion is this log n correction. Of course, it has to be unbounded. So I found myself puzzled by this result, which is well quoted in the literature, like a disproof of the Mertens conjecture. It's a bit misleading, this term, yeah.
A very mesmerizing talk. And I would like to invite our head of our department, Professor P. N. Santosh, to give a small token of appreciation.
Okay. Thank you very much. Okay. Cheers.
So next week, I just wanted to tell you, on Monday evening at this venue at 5 p.m., we convene again for the screening of the movie, Chandra and the Journey of the Star. On Tuesday, in HSB 210, we'll have a starting of a 2-lecture series by Professor Mussardo on integrability in quantum field theories. The first one will be introductory, and then the second will be more advanced. That will be at 4:30 p.m. HSB 210 on Tuesday, and then next one on Thursday. If otherwise you would like to interact with him, just drop me a mail or see me in my office, and we can find a time where we could have a discussion with him. Thank you so much for coming.
Thank you.